Hello, this is Math Jazz from Almost Cool. This is our first attempt at a live stream episode to answer your calculus questions. If you have any calculus questions, you can email them to me at mathjazz9@gmail.com. Let me put that on the screen. Email questions to mathjazz9@gmail.com to have them answered on air. And here is welcome to the live stream. This is live stream episode 1. So, again, if you have any questions, just email them to the, I guess the address is still on the screen. It's down here, right here. And if no one is giving any questions, I have a list of a few questions to talk about. We'll just leave the email on the screen for just a little bit. Our first question, which is going to be coming from my list of pre-made questions, is going to be, let's get the title off the screen. So, the problem is when a rock is dropped, not dripped, but dropped into a pond, a circular wave is formed. If the wave moves at, let's say, 10 centimeters a second, how fast is the circumference of the circle increasing? That'll be our part A. So let's make this part A. And part B is going to be how fast is the area increasing? So the first thing that we're going to have to do is we're going to have to model this circle. So let's do let me draw a diagram. We'll make a circle. The equation for a circle is going to be sine of theta comma cosine theta and theta will vary from 0 to 2 pi. Sorry. There we go. Here's our circle. Now it has a radius that is going to go from the center of the circle to the outside. It also has a circumference and it has an area. And the equations for these are as follows. Going to have the area is equal to the radius times, the square of the radius times pi. And the perimeter, or the circumference, is equal to 2 pi times the radius. So, in our part A, the first, I don't know what that symbol is, and I don't know if I can get rid of it. So the first question is how fast is the circumference increasing? Well, that's going to require us to take a derivative of the circumference equation here. So there we go. We get the derivative of the circumference is equal to 2 pi times the derivative of the radius. Which means that since our radius is increasing at 10 centimeters a second, we get that c prime, that's the circumference, is changing at a rate of 2 pi times 10 centimeters per second. Or 20 pi. So that's part A. It's a very simple related rates problem. For part B, we do the same thing, but we do it with the area equation. So we're going to get the derivative of area is equal to 2 pi times the radius times the derivative of the radius. We have to use the chain rule. And so, with this, we actually can't tell how fast the area is increasing without also knowing the radius, because the rate that the area is increasing depends on the current radius. So for us, we're going to get a prime is equal to 2 pi r times 10, which is going to be 20 pi r. And so if we were asked, say, how fast is the area increasing when the radius is 5, then we could plug in 5 for the radius and get 100 pi. So that is our first question. And we will check the email. And we have no current questions pending in the email, so we'll just move on to the next question that we have in my prepared list. So we will delete this question, but you can rewind and see it again, or you can wait until the video is posted to this channel, and you can watch that again for yourself. Here's question 2. A particle travels along the curve. The reason we use particles, by the way, is because they have no length or width or height or anything. So we don't have to worry about one part of the particle traveling at a different rate of another part of the particle. It makes the problems a lot easier to state. You don't have to worry about like which way it's facing, or this side is turning faster than that one. Now, of course, you can model these more complicated problems in mathematics, or with mathematics, but for first year calculus, we can deal with particles. They're nice and they're simple. A particle travels along the curve y equals x to the 4th power. When x equals 1, the x-coordinate is changing at a rate of 1 unit per second. How fast is the distance from the origin increasing? So we have to come up with an equation that represents distance from the origin. So the distance between a point x, y, and the origin is going to equal, and I'm not sure I remember the shortcut for this command, but we'll just use square root of x squared there we go, plus y squared. So this is the distance from the origin. And so we have to take the derivative of this distance to be able to get the the rate at which the distance is changing, which is the goal. We actually have a choice here. We can take the derivative immediately, like this, or we can use the fact that this particle is on this curve to substitute in for y here. And it really doesn't make a difference one way or the other, so we'll just do it like this. So we have that the derivative of distance is equal to, let's see, I'm not sure I remember how to do a fraction, but we'll have, we'll rewrite this as x squared plus y squared raised to the 1/2 power. So we use the power rule and the chain rule to get that this will be 2 times the square root of x squared plus y squared in the denominator, because our outside function is x to the 1/2 and our inside function is x squared plus y squared. And the chain rule says that you take the derivative of the outside function and you plug the inside function into it. And then you have to multiply by the derivative of the inside function. So we're going to get 2x times the derivative of x plus 2y times the derivative of y. Now the reason that, normally when we're doing implicit differentiation, we don't worry about the derivative of x, because we're taking the derivative with respect to x. But in this case, we're actually taking the derivative with respect to time. So x represents the left-right position on the graph, and let's call the variable t represents our time. So x prime represents how is our left-right position changing with respect to time. In a normal implicit differentiation problem, we wouldn't worry about this because we're not worrying about where something is on the plane at any given point in time. We're just looking at slopes of lines at static curves. So that's why we have to worry about x primes when we're doing this related rate problem. But anyway, if we know that x is 1, we can plug in x is 1 now, and we can plug 1 into this equation and get that y is also 1. And we can simplify this to be 2 times 1 times x prime. So we get 2x prime plus 2 times y prime, but y is 1, so it's 2 times 1 times y prime. So that's 2y prime. And that's our numerator. And our denominator will be 2 times the quantity 1 squared plus 1 squared. So that's 2 times the square root of 2. Now we know one other thing. If we look at our original equation, we know that y equals x to the 4th. But that means that y prime is equal to 4x to the third times x prime. And since we know that x is 1 at the moment that we care about, we know then that y prime is equal to 4 times 1 cubed times x prime. So we can then simplify this derivative of distance further to be 2x prime plus 2 times 4x prime, so 8x prime, divided by 2 square root of 2, which is just going to be 10x prime divided by 2 square root of 2. And this 2 will cancel with a 2 here and leave us with that. Now we know also that x prime is changing at a rate of 1 unit per second. So x was 1 and x prime is 1. So we plug that in and we get 5 over the square root of 2. So we can evaluate that. 5 divided by the square root of 2 is, Mathematica is being cheeky. Let's make it give us a decimal. Here we go. About 3.5 and change. So that's not so bad. Oh, we have a question. I see some activity in the chat. Let us reply to that. Hello, Mark. I'm sorry if it's been a while since you commented. I didn't see you there. Do you have any math questions? Actually, I think the chat is a little bit ahead of the recording, so let's see. We won't wait for Mark to respond on the chat, but I will try and pay more attention to the chat. Let's do another problem. So again, this problem is going to be in the video that'll be uploaded later. Also, you can rewind because I have DVR turned on this recording, so you can rewind up to 4 hours, and this is only an hour-long live stream. So if you want to see this, then if you want to see this, you can either rewind now or you can go back to the channel later and see it again. Anyway, I will delete this question now and move on to the next question. It's good that you don't have any dire math needs right now, Mark. It's I would answer a question if you had one, but not having one is fine. And I'll see you later. Okay, so let's do this problem. So put it into text mode. A camera is placed 2 kilometers from the base of a launch pad of a rocket. Let's move this out of the way. When the rocket is 1 kilometer high, it is moving at a velocity of 300 meters per second. If the camera remains fixed on the rocket, determine the rate at which the angle between the camera and the ground is changing. Okay. So maybe we should draw a diagram of this too. Let's see. I really want a triangle here. So let's say that the launch pad is at 0, 0. And that means that the camera is going to be, we're going to place the camera at 2 kilometers from the base. So, and it'll be pointed up at the rocket, which is at 1 kilometer high. So we want to plot this line. We'll have y equals m, which is going to be negative 1/2. And we want b to be 1. So that is, since the rocket is going to be the x-intercept of our line, we're going to have 1 kilometer represent the position of the rocket. And since the line has to also pass through the camera, then the camera is going to be the x-intercept, and that's going to be 1 below and 2 to the right of the rocket. Now let's plot this from x is -1 to 3. Oh, that has to be in an evaluation cell. There you go. There we go. Maybe we'll make it a bit thicker to be easier to see. There we go. So our rocket is going to be at this point on the graph, and our camera is going to be at this point on the graph. And we want to measure the angle between this line and this line. So to do that, what we see is that this is the hypotenuse and this is the adjacent. So the cosine of this angle is going to equal this length divided by this one. So the way that that gets represented is cosine of theta is equal to the distance between the rocket and the camera, which is going to be the height of the rocket. Well, we're going to use the Pythagorean theorem here to get the hypotenuse. So we get the square root of the height of the rocket squared plus the distance from the launch pad to the camera, which is going to be 2, and we square that, so we'll get 4. So this is going to be the length of the hypotenuse, and we'll divide that by 2, which is the length of the adjacent side. Sorry, let's switch that. Or let's switch to secant, because we don't want to divide by the square root of the square of our variable. So we'll have the secant of theta is equal to the square root over 2. So the secant is going to be the hypotenuse over the adjacent side. And this removes any sort of negative exponents when we take the derivative, because we'll have to take the derivative. So now that we know this, we can go on to say that secant theta tangent theta, we're just taking the derivative right now, is equal to, and this will be the derivative of the other side, so we get the denominator will be 4 square root of y squared plus 4. And then the derivative of y squared plus 4 is going to be 2y y prime. Oh, and we forgot to put a theta prime here. So, let's move this over. So, we just took the derivative of the relationship between the angle and the height of the rocket. And so that gives us this coefficient, and then the rate of change of the angle is equal to this expression that contains the rate of change of the height of the rocket. So, going on, we can actually plug in values here. So we know that the secant of theta is going to be this length here, which is 2, divided by this length here, which we can calculate because we know that the rocket is 1 kilometer high. So this length is 2, and this length is 1, which means that the hypotenuse is going to be square root of 3. And our secant is our hypotenuse divided by our adjacent side. So we're going to get the square root of 3 over 2 as our secant. Our tangent is going to be the opposite over the adjacent. So that's going to be 1 divided by 2, or just a half, equals 2 times y. Well, y is 1, so that's just 2, times y prime, which we know is going to be 300 meters per second, which is 0.3 kilometers a second. We have to use the same units here, so we're going to plug in 0.3. Conversely, we could have written the whole thing in meters, in which case our diagram would have a y-intercept of 1,000 rather than a y-intercept of 1. That is 1,000 meters rather than 1 kilometer. It doesn't matter what units you do it in. We could have changed the whole thing into inches and feet if we really wanted to, but that is much harder than it needs to be because conversion between a meter and a kilometer is not so bad. Converting between meters, kilometers, and inches and feet is going to be bad. But anyway, so we chose to do this in kilometers, and so we need to make sure that our speed is in kilometers per hour, or sorry, kilometers per second, not in meters per second. So we have a 0.3 there. We divide it by 4 times the square root of y is 1, so y squared is 1, plus 4 is going to be 5. Oh, and I forgot to put our theta prime in there again. And then we just solve for theta prime. So we know that our theta prime is going to equal 2 times 0.3 divided by 4 times the square root of 5. And then we're also going to divide by, let's put these in here, the square root of 3 over 2, and divide by half. Now that's the same as multiplying by 2, but I'm just going to plug it in like that. So this is our value for theta prime. And when I execute the code, I get 0.154919. This will be the rate of change of the angle, and it'll be in radians per second. So my decimal values of fractions of pi might be a little weak, but I think that that's maybe, is it pi over 6 or something? No, because pi over 6 would be closer to 0.5 radians. So it's some fraction of a radian, a small one at that. Anyway, let's check again to see if we have any questions on the line. It does not appear that we have any questions on the line. But that's okay, because we have more questions in more questions prepared on the list. So let's delete this one, and we'll go to the next one. So we'll have so let's have our conical pile of dirt. Let's see. So we have dirt is being dumped into a pile, a conical pile. It's nice that, these physical objects behave really nicely in math problems. This will be a conical pile such that the radius of the cone is always equal to 1/3 the height of the pile. If the dirt is being added at a rate of 1 cubic foot per minute, at what rate is the height of the pile growing? Well, the first thing to know is the equation that relates the radius and height of a cone to the volume of the cone. So I'm going to double check that because I have the time to. It's pi r squared h divided by 3. So 1/3. That's volume equals 1/3 of the radius squared times the height. So we're going to take well, we could either take the derivative now, or we can use the relationship between the radius of the cone and the height of the cone. In fact, I think that we should probably do that. So the height of the cone is always going to be 3 times the radius. So this is going to be 1/3 times r squared times 3r, which is going to be just r cubed. Now we have a relationship between the radius and the volume. We could have killed off the h, but I didn't want to have a fractional power. we're going to have to deal with it eventually, but I'm procrastinating that. Anyway, so now that we take the derivative, now we take the derivative, we get v prime equals 3r squared, r prime. We know that the dirt is being added at a rate of 1 cubic foot per minute. So that gives us 1 is equal to, oh, we needed one more part of the equation. At what rate is the height of the pile growing when the radius is, how high is it? When the radius is 3 feet. There we go. So we get 3 times 3 squared times r prime. So that means that r prime is equal to 1 over 27. Now, from this, we wanted to know how fast the height is growing. We can use the fact that the radius is equal to 1/3 of the height to give us that the derivative of the radius is equal to 1/3 of the derivative of the height. But that gives us that 1 over 27 is equal to 1/3 of the derivative of the height. And we multiply both sides to get by 3 to get 1/9 is equal to the derivative of the height. So when the radius is 3 feet, the height is growing by 1/9 of a foot every minute. So 1/9 of a foot, I guess, is, well, 1/3 of a foot is 4 inches, so 1/9 of a foot is 4/3 of an inch. So, I mean, a cubic foot of dirt per minute is quite a lot of dirt to move with a shovel. Not a lot of dirt to move with, say, a bulldozer or a backhoe or something. So, so that is that question. Now, let's see. Let us take some time to just practice taking some derivatives. So, we're going to take the derivative of sine of e to the x squared plus x. This is a chain rule problem. So the first thing that we are going to want to do is identify the outside and inside functions at each step. So sine of x is going to be our outsidemost function. Inside of that we have e to the x. And inside of that function we have x squared plus x. So what we're going to need to do now is take the derivatives of each of these. So the derivative of sine is cosine. Let's give us a little bit of space here. The derivative of e to the x is e to the x. And the derivative of x squared plus x, let's see if I can there we go, is going to be 2x plus 1. So the way that we use the chain rule to find this derivative is we're going to take this function here, and we're going to plug this function into it, e to the x into it. And then we're going to plug x squared plus x into the e to the x. So we get cosine of e raised to the x squared plus x times, and we move to the next function in our list here, e to the x, and we plug in this function here, x squared plus x. So we get e raised to the x squared plus x. And then we're done with this function. And we move on to this final function at the end, and we multiply by it. So we get 2x plus 1. And this cosine of e to the x squared plus x times e to the x squared plus x times 2x plus 1 is our derivative. So that was a nice example of the chain rule. Let us use the product rule now. So we're going to have e raised to the x times sine of x times arctangent of x. So we're going to use the product rule 2 times on this. Actually, there is a 3-way product rule that we can learn. But we're going to use the normal product rule first, and then we'll talk about the 3-way product rule, and then we'll talk about arbitrary product rules. That is to say, any number of things being multiplied together. So this function here, to take its derivative, we're going to have to split it up into 2 pieces. I'll split it up like this. So we take the derivative of the first chunk, e to the x times sine x. I'm just going to write a prime there because that's a product, and we'll get to it in the second step, times the first function, which is arctangent of x. And then we're going to have to remember what the derivative of the arctangent is. And derivative of arctangent is going to be 1 over 1 plus x squared. So we get the first function, which is e raised to the x times sine x times 1 over 1 plus x squared, or x squared plus 1. And now we've simplified this one step. The next step is to figure out what the derivative of e to the x sine of x is. And so we take the first function's derivative, which is e to the x, and we multiply it by the second function. And then we add the first function, which is e to the x, times the derivative of the second function, which is cosine x. That's the derivative of e to the x sine x. And then we multiply this by arctangent. Of x. And we add, we're just going to copy paste this here. So this becomes the derivative of cosine the derivative of e to the x times sine x times arctangent of x. But now we'll talk about a we're talking about a three-way power rule now. Three-way product rule now. Turns out that if we have here we go. Nope. If we have three functions, f of x times g of x times h of x, and we want to take the derivative of this thing, the derivative is going to equal f prime of x times g of x times h of x plus f of x times g prime of x times h of x plus f of x times g of x times h prime of x. So each function, f, g, and h, gets a turn at being the only derivative in a term where that derivative is being multiplied by each of the other functions. F prime gh, f g prime h, and f g h prime. In general, this works for as many functions being multiplied together as you'd like. If you have 5 functions, then you're going to have 5 terms, and in each term, each of those 5 functions is going to take a turn being the one whose derivative you've taken. So we will use this three-way product rule and show that it gives the same answer as the regular product rule. So our derivative based on this three-way product rule should be the derivative of e to the x is e to the x times the other two functions are sine of x and arctangent of x. And then e to the x times the derivative of sine of x is cosine of x times arctangent of x. And the last term is going to be e to the x sine of x, and then 1 over x squared plus 1. If we notice, if we just multiply this arctangent here by these two terms, if we distribute the arctangent, we come up with the same answer that we got here. So that's kind of nice. And it works for any number of functions being multiplied together where you need to take the derivative of that product of functions. Okay, so let's do another example where we have to use the product rule and the chain rule. So let's say we're going to delete all of this from the page just to clear everything up. So we're going to have e raised to the sine x times, let's say, x cubed plus 2x plus 5. That'll be a product rule and a chain rule. And we can add one more term. Let's say we have a trig function. We haven't seen on any logarithms recently. So let's do the natural log of x squared. There we go. Or x squared plus 1. There we go. So we're going to take the derivative of this. This is going to require a three-way product, or the derivative of a three-way product, and it's going to have the chain rule at a few different steps. So let's do this. Actually, the best way to do this is going to be using logarithmic differentiation. So let's see an example of that actually. So this is our function y, and we're going to first take the natural log of both sides of this expression. So we have the natural log of y is equal to the natural log of this thing. But then we realize that we can split products apart when they're arguments of logarithms. So we have e raised to the sine x plus we have the natural log of this polynomial x cubed plus 2x plus 5, and we have the natural log of the natural log of x squared plus 1. So the natural log of y is equal to this. Now, well, I need to close all of my parentheses. But we can simplify even further. The natural log of e to the sine x is just sine of x. And we might be able to factor that polynomial. I don't particularly care about that. And we can't really simplify the natural log of a natural log. But we simplify a little bit more. So now we can take the derivative of both sides of this expression. So we get y prime over y is equal to the derivative of sine is cosine of x. The derivative of 3x plus, x to the third plus 2x plus 5 is going to be 3x squared plus 2. And we divide by the original function, which is x cubed plus 2x plus 5. And then the derivative of the natural log of x squared plus 1 is going to be the derivative of x squared plus 1, which is 2x, divided by x squared plus 1. And then this whole thing is divided by the natural log of x squared plus 1. Like so. Now, if you're wondering exactly how I did that, we notice that the outside function is the natural log of x. The next function in is also the natural log of x. And the function inside of that is x squared plus 1. So the derivative of the natural log is going to be 1 over x. The derivative of the natural log is 1 over x. And the derivative of x plus 1 is 2x. So we plug this function, x squared plus 1, into the natural log, which we then plug into 1 over x, getting 1 over ln of x squared plus 1, and then we multiply by 1 over x times x squared plus 1. 1 over x with x squared plus 1 plugged into it. So that's 1 over x squared plus 1. and then we multiply by 2x. So I'm just going to put that in front here, 2x. But multiplying fractions, we can multiply across. So the top of the first fraction is 2x. The top of the second fraction is 1. 2x times 1 is 2x. The bottom of the first fraction is natural log of x squared plus 1. The bottom of the other fraction, the denominator of the other fraction, is x squared plus 1. So we get the product of those is going to be x squared plus 1 times ln of x squared plus 1. And just to make this a little clearer, let me put it here, and then I will convert to traditional form. There we go. This is what our final fraction should look like. Anyway, that wraps up our first live stream. It was nice to have Mark comment. Maybe I should figure out a way to pipe the chat to the screen, although I also don't want to have to worry about what people say in chat. Some live streamers have some pretty rowdy chats. I don't know how rowdy a channel devoted to answering calculus questions would get. I don't know. But it was nice to have an audience, and it was nice to have some interaction on the chat. So I will see you next week. Next week the show will be on Thursday at 6 o'clock. So I will see you then. So thanks for watching.